From game development to high-frequency trading, thanks to QDC, the Quantitative Developer Certificate.
Okay, my name is Sherry, and today I will be speaking about cross-platform floating point determinism. Those of you who know me already probably know that determinism in general is a subject I'm genuinely obsessed about. When speaking about determinism, I see it as a pretty level field with two big holes in this field. One of the holes is multi-threading. Achieving determinism with multi-threading is extremely difficult, but fortunately we won't need to discuss it today. And the other big hole in determinism is cross-platform floating point determinism, which is exactly the subject of this talk of mine. First of all, I should say that this research is actually not only mine, that there were 7 people involved in it. There was a lot of work. And all of us come from the company, which is nicely named 6 Impossible Things Before Breakfast. And I see that the company name is quite relevant here, because achieving cross-platform floating point determinism was deemed to be impossible at least for 15-20 years. So we see it as one of those 6 impossible things we are claiming in our name. That achieving it is one of those 6 impossible things we are claiming in our name. Okay. Here is the talk outline. First, we will discuss what is determinism and why it is important. Second, there will be some quotes from people who tried to achieve cross-platform floating points determinism in the past. Then I will describe our first attempt, which actually was a failure, but we learned a thing or 3 out of it, so it was useful. Then we will discuss our new approach and working versions. Actually, there are 6 of them. Then I will come to the question of performance. Determinism doesn't come for free, it comes for a price, so performance is important. And then we jump to conclusions and to our C++ standard proposal with regards to floating point, which surprisingly still has chances to get into C++ 26. Okay, first let's define what we are speaking about. Actually, determinism has several possible definitions, and we will be concentrating on 3 of them at this time. So the first definition is that we tell that program is deterministic if given exactly the same inputs, the very same executable behaves exactly the same. This one is fairly easy to achieve, saving for things such as initialized variables and multi-threading. The second definition of determinism is that executables which are built from the very same source code but built for different platforms behave exactly the same given the same inputs. This one is possible for usual arithmetics. Actually, it's possible for pretty much anything besides floating point. For floating point, it becomes a very difficult task, which, as far as I know, nobody really solved before us. The third definition of determinism is actually even more important. It means that the same function behaves exactly the same way in different contexts. And apparently, especially for floating points, and given that we are living in inline all world, it doesn't necessarily stand. The very same floating point function can return different results if it's called from two different places in the code. And this is a big problem, actually. So why those determinisms are, according to different definitions, are so important? Well, the first one, which is the same executable determinism, is important because we want to preserve general sanity, and also because we want to have testability. If on each run we produce different results, it's very difficult to make a reasonable test for it. The second definition, which is cross-platform determinism, is extremely important for distributed simulations, including online games, especially RTS. Just yesterday, there was a talk by Elias, who is present here, who described his own game, which was relying on determinism to reduce amount of traffic which goes between servers and clients. And this idea is indeed very solid. However, for it to work in his context, he had to rewrite all his simulation to fixed point, because otherwise he won't be able to achieve determinism across different platforms, which was his task definition. And actually the third definition, determinism in different contexts, is even more important because it goes to algorithm correctness and avoiding catastrophic cancellations. Actually, we learned about it the hard way. At some point, we had an algorithm which was operating in 2D space, and we ran into a situation when there is a line and there is a point near the line, and near means that sometimes the point fell within rounding margin, so it was really close. And for the purposes of algorithm, it wasn't important whether the point was on the left side on the line, or whether it was on the right side of the line. What our algorithm did not like is when it appeared on the both sides of the line at the same time. At this point, algorithms start to fall apart. And it happened exactly because we called the same inline function from two different contexts, and it was providing subtly different results in different contexts, in spite of arguments being exactly the same. And more generally, we found that there are algorithms out there which are solid mathematically, which are solid when we consider them as fixed point algorithms, but which fall apart when we consider them from floating point of view. And this is fairly obvious if you think about it. It is because in floating point world, unlike in mathematics and unlike in fixed point, there is no such a thing as associativity with regards to addition. Whenever we are making additions in floating point world, there is an implicit rounding after each addition. And this rounding operation is not linear is not linear with regards to addition itself. So order of additions really matters in floating point world, and it's not the case in mathematics, and not the case in with fixed points. Most of the time, such algorithms can be rewritten to make it solid even in case of floating point, But to make them solid, we need to have our floating point correlations to be deterministic. Otherwise, even attempting to reason about it becomes outright impossible. Oops. Okay. So now let's see what people who spend quite a bit of time trying to deal with cross-platform floating point determinism have said. The first quote is by Glenn Fiedler, who is a guru for online simulations and network and passing it over the network. And as far as I know, he is the guy who was hired to rewrite network code of Overwatch to make it work. That's what he said about the floating point determinism. It is incredibly naive to write arbitrary floating point code in C or C++ and expect it to give exactly the same result across different compilers or architectures, or even the same results across debug and release builds. The next quote goes, if you store replaces controller inputs, they cannot be played back on machines with different CPU architectures, compilers, or optimization settings. The next one, experiments are usually reproducible only on the same machine with the same system library and the same compiler using the same options. The next one, cross-platform synchronized network simulations or replace will not be possible. The next one, expecting repeatable results in real programs is crying for the moon. The most optimistic quote in this regard goes back to the same Glenn Fiedler, who said that with a good deal of work, you may be able to coax exactly the same floating point results out of different compilers or different machine architectures. And I can tell you how this problem was usually tackled. You write just your usual floating point code, then you run it on different machines, then you realize that there is a discrepancy, then you try to figure out what's going on, you try to fix it, then you just pray that there are no further discrepancies and that the new version of the compiler will not introduce new optimizations which will break your currently working code. Apparently, I'm not aware of any such attempts which reached production. So lots of people tried, but when going to the production setting, all of them failed. And actually, all such attempts were deemed completely hopeless around 15 years ago, so there is, as far as I know, there is nothing which happened since that time. Okay, so of course we knew what we are dealing with here. And we have set a seriously ambitious set of goals. And those goals are the following. First one, it has to be out-of-the-box solution. It should just work. It should not require whoever writes mathematical code to care about determinism. Or at least we should give hints how to fix it in advance before they run into discrepancies. There should be a method how to write deterministic floating point mathematical programs. Second, we want to be consistent across all modern CPUs. Fortunately, there aren't too many of them these days. What we care about is x64, ARM64, RISC-V 64, virtual CPU of WebAssembly, and in the future we would like to also to get to S390X, that's mainframe one, and Power. Those last two are the last ones which of those CPUs from Unix era. All others are already discontinued. They might work, but making them deterministic is not within our scope. We just welcome pull requests in our repository, which will make it happen, but we are not going to spend time on it ourselves. The third goal is to support at least 3 major C++ compilers. Of course, these are GCC, Clang, and MSVC in no particular order. The fourth the fourth goal, as determinism doesn't come for free, it would be really nice to allow combining deterministic and non-deterministic code in the same executable. Because if you need to mess with compiler flags, it will affect your whole executable. And for example, in the game by Elias and in a game engine which we design ourselves, the code is split into simulator, which has to be deterministic, and rendering, which does not need to be deterministic. And making the whole executable having pretty strict compiler flags, which also affect performance of the renderer, is not the best idea performance-wise. Number 5, we want to provide different performance versus guarantees options. Not all the solutions can work in the all environments, and it is, as we will see, there are different contexts and different requirements, so different solutions might be better for different tasks. And of course, number 6, we have to have extensive testing, because especially for this kind of things, it's not sufficient to just try 2 or 3 functions. We need to try a whole bunch of real-world algorithms, mathematical algorithms. So yes, we are aware that this set of goals is extremely ambitious, but well, that's where the name of our company comes into play. We love challenges, and we love doing things which are considered impossible. So, with all very ambitious goals in mind, we started our analysis. And actually, achieving determinism is really simple. It's like this. You just need to eliminate all sources of non-determinism, and you are deterministic. The tricky part is how to do it, of course, but the idea is very simple. And apparently, for the floating point non-determinism, there are 3 sources. One is CPU. If CPU processes the same addition instruction differently, then we won't be able to use hardware floating point. And by the way, when speaking about exactly the same, we are speaking about producing exactly the same results down to the very last bit with all possible inputs. Because at the very moment when we have discrepancy even in the last bit of mantissa, it will start to accumulate and will cause macroscopic changes sooner rather than later. So we need to have absolute bit by bit correspondence. The second source of non-determinism is compiler. Compiler's job is to make things to run fast. So whenever it sees an opportunity, it will use it. And this causes, in particular, rearrangements, calculating things in different order, because compiler decided that it will be faster. But as we have seen, order of addition matters, and it can cause discrepancies. And another major source of non-determinism is so-called fused operations, in particular FMA, fused multiplication addition. It's multiplies and adds, yes, but the result is subtly different from performing separate multiplication and addition, because usually FMA does not do rounding, at least not at the same size as we would expect it. So result of FMA is usually different from the one of the multiplication followed by addition. And there is a third source of floating point non-determinism, which is often overlooked, is mathematical library. Whenever you call a function such as sine, or exponent, or logarithm, actually you're calling the system function or function of C library, and they tend to be unique they have to be different for different platforms. And unfortunately, as far as I know, IEEE standard does not specify exact behavior of such functions, though it does specify exact down to the last bit behavior for the basics for operations, arithmetical operations, plus, minus, multiply and delete. So yes, libraries is a major source of non-determinism. Now let's see what we can do about each of those sources. Fortunately, modern CPUs and even MCUs actually do provide IEEE 754 compliant instructions. It is indeed specified down to the last bit, and indeed, in theory, according to our testing, they are compliant indeed. Of course, there is always a room for a potential bug, hardware bug, like infamous FDIV bug, which was observed in production Pentiums around 20 years ago. However, hardware folks are assuring us that they learned from that bug, and now they have much better validation mechanisms for the hardware, so it does not look too likely. But it's always a possibility. We are relying on, to do things fast, we need to rely on hardware. There is no way around it. And now, how to handle compiler non-determinism. As I mentioned, a compiler tries to use non-compliant instructions in the name of speed. The question is how to force it not to use those optimizations. And it is apparently possible, and we found more than one way to do it. And as for the library, avoiding non-determinism is actually as obvious as it is time-consuming. We just need to make our own library, mathematical library implementing all those functions, and using only 4 basic arithmetical operations to implement it. However, it's not as bad as it might look, because all actually existing libraries already doing it. So any kind of library uses just basic operations to get approximation. One well-known approximation is Taylor series, but actually it's not always used. But in any case, whatever is used is always based only on those 4 operations. And as I noted before, those operations are indeed compliant on all major CPUs we tested, which gives us hope. Okay, with all this in mind, we came to our take 1, our attempt to tackle this problem. What we tried to do is to adapt existing library to become deterministic. And also we made an assumption that semicolon guarantees sequencing. Actually, there is an interesting rule in C++ standard which says that whatever goes before semicolon should be calculated, including its side effects, before anything which is done after the semicolon. It is the same rule which we use to deal with, let's say, increments in expressions. If we increment the same variable within expression, not separated by semicolon, it's either you be on undefined value, undefined result, I don't remember, but it doesn't matter. But it's a bad thing, we don't write it. How we write it, we separate it into statements and put a semicolon in between, and sequencing rule is what actually allows us to do it. So we also assumed that semicolon prohibits compilers from reordering or fusing operation across the semicolon. That was our assumption here. And if we rely on this assumption, it means that if we place enough semicolons, the code will become deterministic. So if we have ambiguous a plus b plus c, we can rewrite it into unambiguous form which uses a temporary. It doesn't really matter which addition we do here first. It's important that we just specify the sequence, and we assume that if we write it this way, it should be done this way on the same compilers due to the sequencing rule. And if it stands, then we could write static analyzer to find potential non-deterministic ambiguous statements, then it would flag it, and then we would rewrite them into the unambiguous form, and we would be deterministic at that point. All of this sounds really nice in theory. However, not everything which sounds nice in theory goes well when it goes to reality. The problem is, as always, is about assumption. Assumption is the mother of all problems, as always. So apparently, we assume that semicolon prohibits reordering around it, but our testing has shown that at least for two compilers, there are sets of flags which do allow compilers to do FMA across the semicolon. And then we tried to dig deeper into the standard, and we found that even within WG21, there is no obvious consensus about the standard in this regard. Wording of the standard, current wording of the standard is extremely vague when it comes to floating point. It says that floating point is implementation dependent. And it can be read that it even allows implementation to provide different results in different contexts, which is kind of crazy, but it's not clear whether it's explicitly prohibited by the standard or not. Okay, however, in spite of our take one being a failure, we learned a few things out of it. We found that our idea of adapting existing library to become deterministic is a good one. We found that we managed to tackle both CPU determinism and lib determinism, and it is only compiler determinism which we have at our hands before the Holy Grail, before reaching the Holy Grail of the cross-platform floating point determinism. We found that both reordering and fusion, multiplication, addition are big problems in practice. We also found that bug chasing and trying to figure out those pieces in essentially mass level code, which should be changed, is very error prone and time consuming, so it's better to avoid it. And also we found that performance hit of going deterministic is significant. And once again, we notice that we need to allow mix and match of deterministic and non-deterministic code. But what if we have the same piece of mathematics which needs to be used in two contexts, in deterministic and non-deterministic? And fortunately, within C++, there is a beautiful mechanism which is perfect for this purpose. It is, da-dam, of course, templates. Of course, it's templates. So what we decided to do is that we have to rewrite the same MUSL or whatever, but we took a MUSL library, we templatized it this time. So instead of using floats inside, we made it templated on type name FP, which can be a float, and then it will produce exactly the same results. Or it can be our own class, which looks like a duck, quacks like a duck, and behaves otherwise like a duck, except that it is deterministic. And apparently rewriting was not that difficult. It was very straightforward. We managed to rewrite it line by line, with only replacement being cosmetic. And actually, one of our guys was able alone to rewrite the whole library, to templatize the whole mathematical library with all the functions such as sine, cosine, log, log10, atan, atan2, and whatever. in just 3 days. So it's an effort, but it can be done. It's perfectly doable. But actually, you won't need to do it because we already did it. And while we are at it, we also have our own geometry library, and we templatized it too. So, what matters here is that the code looks really straightforward. There is absolutely no any trickery related to the determinism here. It's just plain good old code. The only thing is that if we will want to use our fixed point improvement, which I will discuss later, we should use auto as time for dx and not fp. But that's basically the only thing, and well, it's still perfectly valid code anyway. Okay, and this really matters because, you will need to write your own code using the same approach. But it's still very straightforward, and it's also very possible to convert existing libraries to this thing. Okay, and now we found that we can write not 1 but 6 of the types which can be used as FP template parameter in all the math, including geometry, including sign and whatever. And those types are the following. The one which is guaranteed to work is so-called soft float. It is trying to simulate a behavior of IEEE using just integer math. However, so we based it on literally amazing Berkeley soft float library. However, in spite of being amazing and in spite of the guys being geniuses, it's still roughly 5 times slower than hardware floating point. And it's not surprising because of the amount of things they have to do. Even simple addition requires you to find the difference in exponents, to find how much to shift one of them, to add, to round, so lots of things are going on, and actually that they managed to do it in just that few CPU cycles is a miracle. But it's still 5 times, so we have to look for something else. While 5 times can be acceptable in some contexts, in some contexts it will be way too much. Our next idea was to use a shared library. Actually, if we put those 4 basic operations into DLL or SO, then compiler will not be able to see through the boundary with the DLL, so it won't be able to try to optimize it out. To merge, for example, it won't be able to merge it with anything because it doesn't know what it is there. So that's one way of doing it. And another way of doing it is a static library or just a separate CPP file. Then it is about the same, but we have to disable LTO. Unfortunately, for those 2 approaches, we also effectively disabling inlining. And inlining is a prerequisite to any very performant code, as we will see from it. It will be confirmed by performance testing I will show later. The next one we will be dealing with is inline assembly. Actually, when we have inline assembly, we are basically telling the compiler, just shut up and do what I tell you. I know better. And compilers usually respect it. We didn't find any examples otherwise, and just doing as instructed. And the beautiful part of it is that it can be inlined, and moreover, when running in inline assembly, we can specify that that compiler is free to use any registers. In this case, its register allocator will be able to work, compiler will be able to optimize, but within those 4 operations which we wanted to use and nothing else. And that's exactly what we want. Unfortunately, for MSVC, there is no inline assembly for 64 bits. So for MSVC, we had to resort to intrinsics. But for intrinsics, compiler is allowed to re-optimize intrinsics. So it is allowed to mess with all those things which we wrote, do it this way, but it is allowed to do it more efficiently, and it often does it. So we managed to find a way how to prevent it from doing it, but it's a little bit more shaky because it's not guaranteed that in the next version of compiler it won't start to optimize it too. Last two ones are heavily dependent on compiler flags. One is just using strict FP semantics, which is fine, but it's fairly slow. And another one is the same semicolon idea, which apparently we found flags under which it does work. It is just a question of compiler flags. Okay. Actually, most of implementations are trivial. There is nothing difficult in putting a function which adds floats into a DLL or into a CPP. There are only two not so trivial pieces of code. One is related to this semicolon dependent float, and it finally looks like this. For its magic to work, we need to have this semicolon between calculation and returning. And if you see such code without comments in between, quite a few people will just say, oh, what you are doing here, why you are not writing in one single line? And this would destroy the whole concept and destroy all the guarantees we're relying on. That's what we put this really scary comment there. And another non-trivial thing is inline assembly, which is, there is nothing really special about it, but it needs to be written for all the CPUs we are supporting. And we need to be careful about clobbers because this is going to be inlined. But it seems that we did it, and that it means that users of the library won't need to care about it. It was just a piece of work on our side. Okay, now to the interesting stuff, to the testing. So, as we remember, our take one fell apart exactly at the point of testing. So, here are the results of our correctness tests. As you can see, we tested it over 3 different compilers and over 3 different architectures, x64, ARM64, and RISC-V. And as we can see, with usual float as a template parameter, all of them have some cases when behavior is not exactly the same over the platforms. And all our IEEE float FP parameters came with that really nice 0 in the first column. They all were absolutely identical across the board. Moreover, we observed them to be exactly identical even for numerically unstable algorithms. So we found that some of our algorithms in geometry are not really good, and that changing even one single bit will produce vastly different results. But as long as we stayed within our IEEE float replacements, all of them were exactly the same across all those platforms. And of course, having 0 there is a prerequisite to saying that we have determinism, because even one failure is like, forget about it. So here we were nice. Now the next step is about performance. I guess that at least half of you were enduring my lengthy speech only to see this slide. So here it is. Once again, it's over 3 different platforms, 3 different CPUs, 3 different compilers. Results here are the geometric average of 173 real-world CI tests of the mass, of the geometry mostly. And what we observed, and the results are expressed in terms of how much slower it compared to usual float. And yes, all the results are slower than the usual float, but this is to be expected. The question is by how much they are slower. And as we can see, soft float, in spite of all the amazing work which the guys from Berkeley soft float put into it, is still 4 to 6 times slower than float, which is big enough to be a deal breaker in some cases, in most of cases. The next bunch is about shared leap and static leap. Apparently, they are around 2 to 3 times slower than original float, which is still a lot, and we attribute it to the lack of inlining, which I mentioned earlier. An inability to inline things is a big detriment to modern compilers, especially when we are speaking about a function which just adds to floats, which is very fast otherwise. It should be inlined, and compiler cannot. Well, it's going to cost us. Now let's look on the right side of to the right two columns. Those things are flex dependent. Sometimes, as we see, they are fairly efficient. But let's not forget that when we are using flex, we generally should keep the flex the same across the whole executable, so we will be slowing down not only our deterministic code, but also any other code in the same executable, which means that it's pretty often not the best idea. And then we have our best thing is inline assembly. And I would say that it's pretty good. We observed, as you see, we measured the difference is between 10 and 35%, and this is indeed pretty good. Yes, it is slower, but if we really need determinism, quite often it will be acceptable. Okay. A little bit about our further work on trying to improve performance. The idea is to use fixed point for geometry. In general, floating point is not the best choice for geometry coordinates. Floating point has non-uniform distribution of values and therefore errors. And usually, unless we are simulating a solar system, we don't have a special point in zero. So usually when we are dealing with geometry, we are dealing with things which are uniformly distributed, and fixed point is a very natural choice there. Yes, we will need to normalize to bounding box. On the other hand, we were aiming to have a class which can be used as just yet another class, yet another template parameter for the very same mathematics which we already wrote. And apparently to achieve it, we found that we can stay within fixed point as long as we are dealing with coordinates or squares. But at the moment when we are, let's say, trying to divide two lengths and take a logarithm out of them, we don't really know, we cannot possibly know, except for very careful analysis from the application level side, we cannot possibly know what kind of fixed point we would need to express the result. So to have it as a universal replacement, we had to have a concept of fallback type. So it's fixed point as long as we can, but as soon as we cannot say what kind of fixed point we need, we will resort to fallback type. However, as long as most of our operations are a geometrical one, and it's very common to have all kinds of cross products, dot products, all these kind of things, they can be done within fixed point, and it will happen automatically when we just feed this class there, and we will very rarely fall into fallback type, so we will enjoy all the performance benefits of fixed point. And of course, fixed point part by itself is deterministic by design. No problems there. Okay, this is a nice diagram we made to demonstrate it. So fixed point has a template parameter of n, which says how many bits we are using, maximum bits we are actually using out of it. And then if we are trying to add to a fixed point with maximum bit of 31, we will get another floating point type, which has 32 bits and so on. I won't go into details here, but the idea behind is actually the same idea of the excellent CNL library with its elastic integers. However, the difference is that, so the idea is the same. We are calculating return type of operations based on what we are doing. But the difference is that they are trying to stay in fixed point pretty much forever. And we are saying that as soon as we go above 64 bits, the game is over and we are going to fallback type because very long integers are not really fast. So we are trying to keep it within the pretty fast 64 bits. Okay, and here there should have been a slide with performance measurements of fixed point, but unfortunately it's not ready yet, so it stays as work in progress. We will publish it to our GitHub page as soon as we have the results, but for now, sorry, we don't have the results yet. It should be ready by, knocking on wood, 1-2 weeks, but well, as always, you never know in practice. Okay, let's now see what we tried to achieve, those 6 goals we set, and what we did. We said that we want out-of-the-box solution, and yes, we got it. But if you want performance flags may be needed, but still it's orders of magnitude better than it was before. You don't need to chase bugs, you don't need to change your mathematics to become deterministic. So, well, it should be pretty stable, whatever you write there. We said that we want to be consistent across all modern CPUs, and we did achieve it across x64, ARM, and RISC-V. And we are currently working on a virtual CPU of WebAssembly. We said that we want to support at least 3 major C++ compilers. Check. We want to mix and match. Check. We want different options. Check. We have 6 of them, so depending on restrictions of your target platform and your needs, you can choose whatever you want in this case. The last, our goal was to provide extensive testing, but by the very definition, it's not just work in progress, it's eternal work in progress. You cannot possibly say that you are done with testing, especially in a field like this. So yes, we will add. What we will do, we will just, as we will develop our libraries, including geometry and physics, we will add CI, and our CI is already routinely checks it consistently across all the platforms. Okay. Unfortunately, this thing is not a silver bullet, and there are some limitations. And the largest limitation is, of course, that it's not really possible to make existing code magically deterministic. It's not like, okay, you can take your code and you compile it with such and such open, and here it is. Nope, it's not going to work. Templatizing is always possible, and it's mechanistic. You don't need to think about the math behind, but it's a significant effort. Well, in theory, we can try to write a recompiler, but it's more theoretical. And which also means that making third-party libs deterministic is a major effort. Sorry. Well, it's going to hurt. We are trying to provide as much foundation as possible, but of course it will be only a small part of what people need. But hopefully, if this thing is widely adopted, then number of libraries which are written in this style will increase. Third limitation is that performance is inherently worse. Our best implementations provide performance which within 75 to 90% of the float, which is already pretty good for quite a few use cases, and we are working on further improvements. And this is partially mitigated by allowing to mix and match non-deterministic and deterministic code, with non-deterministic one being not hurt by deterministic requirements in another part. And the first disadvantage is that fighting for performance may require messing with compiler flags. Now, after we did all this, we said that it would be really nice to sort out how the floating point behaves in according to C++ standard. Actually, there is our research revealed that there is one big deficiency in the C++ standard, and it is that there is no way how we can write code which for sure avoids catastrophic cancellations according to C++ standard, or to current C++ standard. And this is a major problem for the scientific guys. And here, actually, with time, situation gets worse. Back like 30 years ago, compilers were not as sophisticated, and actually, if you wrote a sequence, it usually corresponded to what really occurred. But now, compilers are getting more and more smart. The importance of this thing becomes it increases. Currently, it becomes more difficult to achieve such things. So, Guy Davidson, present here, and he is also simultaneously a member of our team and a voting member of WG21. He prepared P3375, reproducible floating point results. He also circulated it amongst certain WG21 members, and it got quite good traction. So in the ideal case, which never happens, we may even hope for it to be accepted even C++26. Just knock on wood. Yeah. Keeping fingers crossed, knocking on wood, and whatever we are doing. But it can be yet another major thing for C++26, because not because of online games, but because of algorithm correctness and stability. What is proposed is to have a library class std_strict float, which takes standard float type as its parameter. We don't care how it will be done, by compiler, by a library, by something using both, as long as it exhibits those properties. Apparently in IEEE 754, there is a clause which defines what reproducible is. It's just never been incorporated into the standard, so this proposal just says that for strict float, it should be reproducible according to IEEE 754. And as a good thing, it allows to avoid catastrophic cancellations. For the first time in C++ history, if this is accepted, then to avoid catastrophic cancellation, you just need to convert to strict float, do your magic, do that thing where order matters in a strict float and convert it back. And moreover, as in fact, conversions to strict float and back are no ops in assembly, so it's going to be really cheap. It's just changing the rules, compilers, how compilers treat those types at those places where it matters. And of course, we will be able to use this type as a parameter in our libraries. Just it will be IEEE compliant. with guarantees, but hopefully will behave significantly faster. But at least we established the boundaries where so it cannot be slower than those 10 to 30% which are already achieved. We hope that it will be much less, like 10%, but again, it's we don't see how it will be, but it should be better. Okay, so I hope I said enough so you can start asking questions. Just one last thing is that all the code is open sourced and is available in GitHub by the link which is shown. So feel free to come there. There is only one thing we want to ask you, is that if during your experiments you will find a discrepancy and you will have a repro to demonstrate it, make sure to send it to us. We are committed to analyze all such cases and to make sure this thing is really solid. Otherwise, it doesn't make sense. It either works or it doesn't. There is nothing in between. Okay? Now we have 4.5 minutes to ask questions.
Hello, I think it was a very interesting presentation. In one of the slides you mentioned floating point numbers shouldn't be preferred for geometric coordinates because they are not distributed uniformly. So does this mean these types are not a good option for physics libraries?
For physics library, again, float is not actually that bad for coordinates. It's just that it's not really necessary for coordinates. So yes, float is subtly better because you can basically use only 23 bits out of 32. So if you go in uniform, you have more precision, more range. But it's actually usually a fairly minor difference. So it can be used. It's a little bit better to use fixed point, but usually people don't bother it, and it's okay.
Maybe some side question, why the focus on RISC-V?
Just because, just to be sure-proof, future-proof. So if it flies, we need to be ready. We don't care about legacy stuff such as Spark, but if RISC-V flies, and it already flies on MCUs, then okay, it's nice to have. Plus, it also was the third platform where we could test it, because for these things, 3 is much better than 2.
Thank you very much.
Hello, does SIMD or vectorization change this picture? I'm just wondering if the instructions have the same consistency and reliability.
Vectorization, it's actually FMA, which I mentioned, is one of those things like vectorization, and avoiding vectorization is about the same. So our methods of avoiding to wrestling out compiler out optimizations also effectively remove all the non-compliant vectorization. Technically, compiler, especially speaking about strict float proposal, compiler should be able still to use vectorization. It's just because, for example, in SSE, all the operations on individual elements of vector are still IEEE compliant, at least supposed to be. So it should be able. Whether it's able to use them using our specific implementations, I don't know, at least not with inline assembly one. As for the rest, this is an open question. We don't really care much about it. What we care about is ultimate numbers, and that it should be correct and it should be fast. Everything else is give or take beyond our analysis here.
So the context in my head, excuse me, is that if you're doing the performance comparison and it's 1.3 times, if you're comparing that against the non-vectorized case, like it's going to be a much bigger difference.
We have a whole bunch of test cases. So We didn't just took one artificial case, we just took all kinds of mass, so some of them should be vectorizable, some is not. So as soon as we will expand this test corpus, we should be able to catch one and the others and whatever results. Question of how many of them are vectorizable, how not, is always an open question, but everybody is welcome to do their own test corpus and measure it.
Thank you.
Thank you for a really nice presentation. It was very informative. Do you have some opinion? Are there benefits or there is a need to standardize fixed point arithmetic in C++?
Probably yes, but it's going to be much more difficult because here we have things to refer to. We have IEEE 754 that reproducibility. So basically what we are doing, we're just pulling reproducibility clause from IEEE standard, and for fixed point the whole, so it's going to take years. If there is interest, yes, why not? But
there is a proposal in flight. It's been around for about 8 years now.
Okay, thank you.
When you observed FMA contraction across expressions, did you also observe that with a compiler barrier in between the expressions, or like a no-op?
Sorry, what the question is? Yes, we observed FMA across the
When
boundary.
you were originally looking at trying to make the floating point deterministic, and you looked at separating all the expressions into deterministic expressions, then you observed FMA contraction across expressions, across a semicolon.
Yes.
Did you also observe that with compiler barriers between expressions?
No, we didn't try to set compiler barriers, no.
Okay. Thank you.
Subnormals, are you supporting subnormals?
As so what we did actually, we ran it against stock configuration of CPUs. We didn't mess with any registers, with any pointers, and it's still consistent. Yes, those things can affect the differences. As far as I know, very, without no warranties, as far as I know, they don't support subnormals.
Okay, thanks.
But from our point of view, what matters is that they are consistent in this behavior.
Cool, thanks.
Thanks, interesting talk. On slide 15, you showed A plus B plus C as an example and split it into two different operations.
Yes.
Wouldn't have been a parenthesis enough? Parenthesis A plus B in parenthesis?
Nope. Parentheses are not enough. Standard is the same way as parentheses are not enough to have two increments of the same variable in the same expression. So it's the same rule and the same thing. You need to have a semicolon between those things to have sequences invoked. So basically compiler is allowed to choose execution order within one expression and is not allowed to mess with order of statements. And parenthesis is just an expression. No.
Okay, thank you.
Okay. So sorry that it took so long. Thank you very much, and please try it. And if you find, once again, if you find any discrepancies, please make sure to file a ticket, an issue in GitHub. We will be looking at them and trying to address them. Okay, thank you.